I'll quickly note before we go on to the more abstract operations that to say that A is congruent to B mod M is to say that they have the same remainder on a clock. Okay, so same remainder on an M-hour clock, or they read the same on the M-hour clock. They have the same remainder when divided by M. And that's what we're going to mean by A congruent to B mod M. Straighten the camera out here so we don't look cockeyed. To say that this is equivalent to also saying that the difference is divisible by M. That is, that A is congruent to B mod M means that the difference has no remainder. And the fact that these two are equivalent is fairly obvious. If you divide, let's just do one example. 50 divided by 6 has remainder 2. 98 divided by 6 has remainder 2. So 98 minus 50 over 6 should have remainder 0, and you can check out and see that that is the case, and you might want to be sure you think through why that's the case so you really understand the equivalence. Okay, now we're going to look at an abstract operation. Okay, this is an operation on the set A, B, C, D. And the operation is going to be designated by a star. And we're saying that A star A is A star B is B, A star C is C, and so forth. And similarly for A star A and B star A and C star A and D star A. We get the A, B, C, and D back. And I guess this shows us, doesn't it, that A is an identity? Because A doesn't change anything that it operates with. We don't know what A means or what B means or anything. We simply know that you have this rule for the operation. Okay, now if B operates in A, B, C, D, we get respectively B, C, D, A. And we note that the column for B is the same as the row for B, so that the order in which we operate with B doesn't matter. C and D have similar patterns. Now, really, if we replaced A, B, C, and D by 0, 1, 2, and 3, we'd have an addition table for a 1 hour or for a 4-hour clock. But we're not really interested in that fact. There's no reason this has to be the addition table for a 4-hour clock. We can get much different tables. This operation is closed because we get only A's, B's, C's, and D's when we operate on and with A's, B's, C's, and D's. It's commutative because whatever two numbers we multiply, and we're going to call this Greek capital Gamma and capital Delta, just letting Gamma stand for any of these letters, A, B, C, or D, and letting Delta stand for any of them. If we do Gamma star Delta, it's the same as Delta star Gamma. How do we know that? We know that because the rows correspond to the columns. The row for D is the same as the column for D. All the letters in the same order in the row as they are in the column. Okay, this operation turns out to be associative. We're not going to verify that, but if we take any two letters from the list, say C and B, and combine that with D, it's the same as if we got C and combined that with B and D, the result of B and D. We do have an identity. As we noted, the identity is A And we have inverses. How do we find the inverses? We spot the inverses by noting the things that we combine to get A. The inverses here give us A. It's kind of run together there. My fault. But the inverses give us A. So A with A gives us A, doesn't it? And B with D gives us A. And C with C gives us A. And of course, D with B gives us A, which we already know because we saw that B and D gives us A. So that this operation has all these properties. Here's another operation. What properties does this operation have? Well, we can see pretty quickly that this row and this column show us that we have the identity, and that identity is A. Do we have commutativity? Let's see. The row for B is BDAC. The column is BDAC. So we're doing okay so far. CADB is the row for C. CADB is the column for C. The row for D is DCBA. The column is DCBA. Yes, it's commutative. Inverses? A and A are inverses. Let's see, if we look at the table, we see that B and C are inverses. And we see that D and D are inverses. And of course C and B will also be inverses. So is this the same operation we had before? Well, not quite. We see that B and D are inverses here, where B and C are inverses here. And there are other differences in the operation. But we do have the inverse property. Everything has an inverse. Associativity. Let's just check one possible combination. Let's check D. Now the name of the operation is square. D square C square B. And see if that's the same thing as if we do D square C square B. Is this the case? Now, if we look here, we see that, let's see, we first have to calculate D square C, and D square C gives us B. So D square C is going to be replaced with B. And what about C square B? C square B gives us A. So right there is what we have to evaluate. Now what do we get if we do B square B? We get D. So B square B gives us D. And what does D square A give us? See, D square A gives us D. Of course, we could have told that since A is the identity. But yes, so far so good. We haven't proven that the operation is associative. We've only proved that this particular instance has that property. If we choose D, C, and B in that order and group them this way and this way, that we do get an identity, that we do get an equality down here. But that doesn't show us what happened if we did D with C with D, or A with B with D, or any of the other many combinations that we can get from the three letters here. Okay, it turns out that there are three there are 4 letters, and we're choosing 3 of them. There are 4 choices for each, and it follows that there are 4 to the 3rd or 64 combinations that we would have to check here. Don't need to worry about that part of it. Just understand that to get associativity, you'd have to check every possibility, or be sure that you had verified in some way every possibility.